Buick Technical Assistance. This is Dave. Can I help you?
Mike speaking. How can I help you?
Larry Schramm.
This is Wayne speaking. This is James Bundo. Can I help you?
Here at the Buick Technical Assistance Center, TAC personnel spend their days helping technicians across the country diagnose some pretty difficult problems.
Yeah, you could swap it and see what happens, but I think your interior lights will still stay on because I'm sure that white wire is probably going to ground somewhere.
Is there any way you can bend those out so you can get a little bit more clearance?
What is the fuel pressure like?
Does it drop down at all?
Okay, the case number on that, sir, is 2245.
Oftentimes, these problems are logged into a database so that they can be tracked or recalled when a similar problem occurs in another vehicle.
Technical Assistance has new extended hours of operation, Monday from 10 a.m. until 7 p.m., Tuesday through Thursday from 8 a.m. until 7 p.m., and Fridays from 8 a.m. until 5 p.m. This helps us better serve our Western customers.
Because the orange wire definitely needs to go on terminal 6.
Today we're going to look at some of the common drivability conditions we've received. For example, supercharged engines, the supercharger to lower intake manifold gasket vacuum leaks, and lint or dirt issue on throttle body mounted mass airflow sensors.
Before we go over some of the repairs that Wayne was referring to, let's cover a few drivability tests that can really cut down on your diagnosis time. The first test I want to cover is a ground credibility test. This test can be performed at any sensor that feeds back to the PCM. I'm going to use the throttle position sensor on this Park Avenue for this demonstration. The first step is to disconnect the sensor. Then, connect the red lead from the DVOM to the TPS ground terminal. It's the black wire on this sensor, but be sure to check the wiring diagram for the other sensors. Connect the black lead from the DVOM to the negative battery terminal. Now, set the DVOM to the millivolt setting and turn the ignition key on, but don't start the vehicle. The final step is to jumper DLC terminals A or B to a ground terminal. You can also use a scan tool to put the vehicle in field service mode. The reading on the DVOM should be 50 millivolts or less. If the reading is above 50 millivolts, the most likely cause is a loose or damaged ground. A damaged ground can include a break in a ground wire, loose connector, broken connector, or a loose bolt. The next test I want to cover is a running compression test. This test is a good way to check for weak or broken valve springs. It's also a whole lot easier than removing the valve covers to visually inspect for this condition. When an engine is running, the RPMs are higher than during engine cranking. Therefore, a weak or broken valve spring will not allow time for the valve to fully close. Perform the test by installing the gauge into one cylinder and letting the vehicle run for a few seconds once it starts. There are no specifications for this test. Compare the readings on several cylinders to check for this condition. Now let's go over oxygen sensor diagnosis and testing. Under normal operating conditions, a good pre-catalyst oxygen sensor will show peaks and valleys in output voltage. The post-catalyst oxygen sensor should always have a steady reading. If a post-catalyst sensor voltage begins to bounce between high and low, it's not operating properly. A post-catalyst reading that shows peaks and valleys in output voltage indicates a failing catalytic converter. Remember, the post-converter oxygen sensor is used to measure the oxygen storage capacity of the converter. Let's test the oxygen sensors on this vehicle. Start the vehicle and connect the scan tool. Enter the snapshot mode. Then select FO as the trigger point. For this test, we want to perform a manual trigger. Next, take a look at engine coolant temperature. The coolant temperature should be between 85 and 100 degrees Celsius. Select engine speed and loop status from the data list. Run the engine at 2,500 RPM for about 1 minute. And then at 2,000 RPM to ensure closed loop operation. Select O2 sensor voltage from the data list. Maintain 2,000 RPM while monitoring the voltage. The reading should be fluctuating between 100 and 900 millivolts. Maintain engine speed at 2,000 RPM and trigger the snapshot. After the scan tool has finished the snapshot, go back to the oxygen sensor volts reading and cycle through each frame of the snapshot. Record the voltage range of each frame of the snapshot on the chart included in the know-how reference manual. There should be 5 marks in area 1, 5 marks in area 4, more marks in area 1 than 2, and more marks in area 4 than in area 3. Trace your readings with the O2 sensor curves in the know-how reference manual. Notice that most of the curve is in areas 1 and 4. This explains why you should see more voltage readings falling within area 1 and 4 than in 2 and 3. Wide, evenly spaced voltage fluctuation indicates that the fuel system is being modulated correctly. If the O2 sensor modulates narrowly in areas 1 and 2, the air-fuel mixture is lean, or the sensor is poisoned. If it modulates narrowly in areas 2 and 3, the air-fuel mixture is being modulated correctly, but the sensor is poisoned. If it modulates narrowly in areas 3 and 4, the air-fuel mixture is rich, or the sensor is poisoned. The fuel pump amperage draw test can be useful when diagnosing fuel pump concerns. High amperage usually indicates a problem within the fuel pump. Low amperage usually indicates a problem within the fuel pump circuit. To perform the test, use a DVOM set to the amp setting. Make sure the key is in the off position and then jumper the fuel pump relay to run the fuel pump. Good fuel pumps should generally be between the following. On throttle body engines, between 2 and 4 amps. On port fuel injected engines, between 4 and 6 amps. And on central port injected engines, between 8 and 9 amps. The last thing I want to cover in this segment is Misfire monitor diagnostic operation. The Misfire monitor diagnostic is based on crankshaft rotational velocity variations. The PCM determines this velocity using the crankshaft and camshaft position sensors. When a cylinder misfires, the crankshaft slows down momentarily. By monitoring the sensor signals, the PCM can determine when a misfire occurs. For a non-catalyst damaging misfire, the diagnostic will be required to report it within 1,000 to 3,200 engine revolutions. For catalyst damaging misfires, the diagnostic will be required to respond to it within 200 engine revolutions. Rough roads can also cause misfire detection. A rough road will cause torque to be applied to the drive wheels and drive train. This torque can intermittently decrease the crankshaft rotational velocity. In order to prevent the PCM from perceiving a rough road as a misfire, the PCM also looks at wheel speed sensor signals. The PCM constantly monitors the signals from these sensors to see if the vehicle is traveling on a rough road. If the PCM sees different wheel speed on several of the wheels, it assumes that the road is rough. Therefore, it does not detect a misfire. Whenever a cylinder misfires, the misfire diagnostic counts the misfire. The misfire counter stores this information. The misfire monitor is basically a file for each cylinder. A current and a history counter is maintained for each cylinder. The current misfire counter indicates the number of firing events in the last 200 that were misfires. The history misfire counter indicates the total number of cylinder firing events that were misfires. The misfire history counter will display the number 0 until a misfire is detected. Once a misfire is detected and the DTC set, the misfire history counter will be updated every 200 crankshaft revolutions. A scan tool can be used to monitor the misfire counter data on all OBD2 equipped vehicles. Knowing which specific cylinders have misfired can help lead to the root cause of the problem. For example, if cylinders number 1 and 4 were both misfiring, the ignition coil that they both share may be the cause of the problem. Keep in mind that the misfire diagnostic may indicate a fault due to a temporary problem, not necessarily caused by a vehicle emission system malfunction. Examples include contaminated fuel, running out of fuel, fuel-fouled spark plugs, or an engine mechanical problem. Now that we've covered some basic drivability tests, let's look into some concerns on the 4T60-E Transaxle. The first transmission concern I want to go over is the TCC slip or shudder condition. There are several possible causes for this condition. The first is a short to ground between the TCC solenoid and the PCM. You can use the Transaxle test-out box to check for this condition. The next cause of this condition is debris blocking the TCC solenoid. A screen was added to the solenoid during the 1992 model year to prevent this condition. Another cause of TCC slip or shudder may be the TCC regulator valve stuck in the valve body. To check for this condition, vary the TCC solenoid duty cycle using a scan tool. If the regulator valve is stuck, TCC slippage will not be affected when the solenoid duty cycle is changed. The final cause of TCC slip or shudder may be a damaged or missing turbine seal. This should be suspected if all the other conditions are not found. Varying the TCC duty cycle will affect but not eliminate TCC slippage. To check for this condition, monitor the transmission pressure while the Tech 1 is applying the TCC. The pressure should be steady. If it is jumping back and forth, this is most likely the problem. Another transmission-related item is driveline vibration at speeds over 35 miles per hour. The condition may be described as a vibration, chuggle, miss, hesitation, or fish bite. The sensation is experienced on vehicles equipped with 3800 engines. It's most likely the torque converter clutch engagement being transmitted through the passenger compartment. The condition can be improved by updating the calibration. Before updating, it's important to note that on cars with cycling compressors, the cycling may be diagnosed as chuggle, miss, or a similar feel. This update raises the third gear TCC lock from 37 to 50 miles per hour and the fourth gear TCC lock from 45 to 54 miles per hour. This calibration update is only for Series 1 and 2 3800 engines. Don't attempt to repair supercharged engines with this calibration. The revised calibration is not considered a 100% cure to the problem. However, most owners will not notice the higher TCC lockup speeds. The first drivability concern I want to go over is spark plug carbon tracking. Air gaps between the spark plug and spark plug wire boot may cause carbon tracking. These gaps can be created when ribbed spark plugs are replaced with the newer ribless plugs. This can be due to formed ribs in the old spark plug wire boot. Carbon tracking can result if there is enough of a gap between the new style spark plug and the old spark plug wire. This is a typical example of what the carbon tracking will look like. If carbon tracking occurs, replace the plug and wire. Another drivability concern I want to talk about is tip-in hesitation on acceleration. Some of these hesitation concerns can be caused by debris on the mass airflow sensor elements. If you look closely at this one, you'll see a few small particles. This sensor was sent in from a technician in Pittsburgh. The debris on the sensor was the cause of his customer's problem. Oftentimes, these conditions are caused by inadequate air filtration. If the air filter doesn't have a tight fit in its carrier, debris may pass through and contaminate the sensor. Check for the brand of filter the customer may be using. Some are better at filtering debris. Also, make sure the filter meets all factory specifications. You'll want to check the owner's manual for the correct filter. Contaminated mass airflow sensors can be cleaned by spraying electrical contact cleaner or brake cleaner on the sensor element and drying it with compressed air. After performing this repair, it's important to disconnect the negative battery cable for a few minutes to clear the PCM's long-term memory. Oh, and incidentally, to diagnose a mass airflow problem, use your scan tool. If the long-term fuel reading goes up under acceleration, mass airflow contamination could be your problem. The next condition I want to go over is rough idle on 3800 supercharged Series 1 engines. Technical Assistance has dealt with many cases where the front part of the supercharger gasket fails and moves towards the intake. We've kind of chewed this one up a bit in taking it off, but this is the failure we're talking about. This results in a poor seal between the intake and the supercharger. To correct this condition, replace the gasket. When replacing the gasket, make sure the sealing surfaces are completely flat and free of any defects or debris. Some signs that this condition may be the cause of rough idle are high, short, and long-term fuel trim readings, or DTC's PO131 or PO171. On older vehicles, look for DTC 44. Another condition I want to talk about today is chuggle concerns on all engines. One thing to check for when diagnosing chuggle concerns is the injector spray patterns. Clogged fuel injectors can cause decreased engine performance and chuggle conditions. When fuel injectors become obstructed, fuel is sprayed onto the walls of the intake instead of the backside of the intake valve. The first step of the spray pattern test on the 3100 is to remove the intake manifold. Then, connect the tester to the battery and the injector you wish to test. Now, relieve the fuel pressure from the system. Release the fuel rail from the intake manifold with the injectors still connected. Rest the rail so each injector sits about 1 inch above its opening. Remember to place a shop rag near the surrounding area to prevent excess fuel from spraying on the engine. Then, pressurize the fuel system. Press the start button on the tester to fire the injector. A good injector spray pattern will be cone-shaped, like this one. If the spray pattern looks like a half cone or a steady stream of fuel leaks from the injector, it should be replaced. Well, I've got the tester hooked up. Let's take a look at how an injector coil check is performed on this 3100 engine. In addition to the tester, you'll need a DVOM to perform the fuel injector coil test. But first, check the engine coolant temperature of the vehicle you're working on, because there are different specifications for warm and cold engines. Now, during the test, the first second of the voltage reading displayed on the DVOM may not be accurate due to the initial current surge. Record the lowest voltage displayed after the first second of the test. The voltage displayed may increase throughout the test as the fuel injector windings warm and the resistance in the windings change. If you see large fluctuations in voltage that do not stabilize, the most likely cause is an intermittent condition within the injector. From the voltages recorded, identify the highest voltage excluding any voltages above 9.5 volts. Then, subtract each voltage that is not above 9.5 from the highest voltage recorded. The subtracted value for any of the injectors should not exceed 0.6 volts. Any fuel injectors with a value higher than this should be replaced. Any fuel injector with a recorded voltage reading above 9.5 volts should also be replaced. Now, let's go over EEPROM reprogramming procedures. EEPROM, or electronically erasable programmable read-only memory, is a type of memory module that can be reprogrammed many times over. Reprogramming EEPROMs is much more efficient than the actual PROM replacement. Rather than physically replacing the PROM, old information is erased from it and replaced with updated calibrations. There are 3 programming methods that can be used to reprogram a EEPROM. They are direct, remote, and off-board. Each of these methods basically accomplishes the same function. Data from a TechLine CD-ROM is downloaded into a EEPROM. These programming methods are accomplished by using TechLine terminals as well as a scan tool, depending on the method and application. Direct programming is when a TechLine terminal is connected to a vehicle's DLC and data is loaded directly into the EEPROM. This method can be used on 95 and older cars. Remote reprogramming requires both a TechLine terminal and a diagnostic scan tool. The scan tool is used to transport the new data from the TechLine terminal to the vehicle's PCM. The final method of reprogramming is known as off-board reprogramming. This is when data is transferred from a TechLine terminal directly to a PCM. This type of reprogramming is generally performed when the vehicle is not available. Since the cooling fans run during reprogramming, you'll want to disconnect them beforehand. This prevents the battery from draining during the process. Battery voltage is critical during reprogramming. If voltage drops below a certain threshold, reprogramming will be aborted. If the reprogramming is interrupted for any reason, the PCM will be ruined. We'll be using a T6 TechLine and a Tech2 to remotely reprogram the PCM on this vehicle. Procedures for some of the other TechLine terminals vary slightly, so you'll want to check the know-how manual for more details. The first step is to connect the scan tool to the vehicle to retrieve the current calibration information. If you're using a Tech1 and VIM, turn the vehicle's key to on before connecting. At the mass storage title screen, press Enter. Select Programming, and then enter the vehicle information. Select Program, and the Tech2 will display Programming Control Module. Press Exit when it's complete. Then disconnect the Tech2 from the vehicle. Select EEPROM from the terminal's diagnostic menu. Select Terminal to Tech2, and then Done. Connect the scan tool to the TechLine terminal using the RS-232 cable. Follow the instructions on the terminal's display. Now, if you're programming a new PCM, you'll want to enter the vehicle's VIN through the New Vehicle menu. Remember, if you're programming a new module, you don't need to retrieve information from the old PCM to perform the procedure. Select OK on the TechLine terminal, and then select the proper calibration file. In some cases, only one calibration file will be available. Then, select Program, and then Yes to begin downloading the files from the terminal to the Tech2. When the terminal is finished updating the calibrations, it will be indicated on the display. Now that the new calibrations are stored in the Tech2, you'll want to connect it to the vehicle and transfer the information to the vehicle's PCM. The tests and repairs we've covered today can really help when diagnosing drivability concerns. Not only will they help cut down on your diagnosis time, they'll probably cut down on the amount of calls you need to make to Buick technical assistance. Remember, the Know-How Reference Manual contains a complete list of tests and repairs. The job aid included in this month's kit can be a handy drivability reference for years to come. I'm Chuck McLennan. Thanks for watching, and we'll see you in next month's Buick Know-How.